Hello. Hello.
And she will be talking about the recent trends in speech recognition. So there are two papers, two lectures to be delivered, and of course the first one will be Professor Jyotis Lal, and he is sparing 15 to 20 minutes. He will be delivering his lecture. Then the interaction will begin. Okay. With these words, um, I leave the floor to the Professor Jyotis Lal. Let him present his.
Okay, sir. Thank you. Thank you very much. I hope I am audible. Okay, sir. So first of all, I would like to thank Dr. Umaraj sir and Professor Rajendra sir for giving me this opportunity to deliver this lecture at the Prestigious Institute, Madurai Kamaraj University. And I also express my sincere gratitude to. So please let me know once it is shared.
Share one. Share பண்ணுறேன்.
Is it clear, sir? Visible?
Yeah, yeah.
Okay. So I'll start. So as I said, this is regarding the detection of dynamical transitions in human speech production. So I would like to acknowledge this PPT and presentation content in the name of Dr. E.A. Gopalakrishnan and Dr. D. Govind, who are my gurus and guides in actually getting me the PhD. And I would like to acknowledge them in giving me the insight on these areas and success on my successful completion of the doctoral thesis also. So straight away coming to the outline of my talk. So I'll be briefly giving you an introduction on human speech production, and then we will try to see the dynamic transition that can occur in the human speech production and how we can accurately detect them, and what is the scope in detecting that dynamic transition, and why do we prefer a nonlinear perspective, and why we need to do a data-driven approach. So these were the point of discussion for the initial part, and then I will also try to address some of the open problems which we have identified in our center, and we solved it, and we were able to get good publication out of that also. And in regard that, we will also say the methodologies and the results obtained in those papers, and especially regarding the characterization and detection of dynamic transition, we will be kind of introducing you regarding some of the techniques like the variational mode decomposition, multifractal different fluctuation analysis, surrogate analysis, etc., which are non-linear and data-driven methods to understand and characterize the dynamic transition in any kind of time series that are not only in speech. Okay, so but we are actually specifically focusing on its application in the speech processing domain. And finally, we will conclude the section with what are the inferences that we got out of these results. So that will be the outline of my presentation. And coming to the human speech production, as we all know, this is actually kind of motivated from biological systems that we have in our human body, right? So I am giving you two perspectives, like the biological perspective and the mechanical perspective of human speech production. So if you talk about how a speech signal is produced, I can answer that in two perspectives. That is, one from a psycholinguistic perspective and one from a functional description. That is, from a psycholinguistic perspective, if you see, human speech is kind of generated or created out of the brain itself. That is, your idea for speech is generated out of brain, and it actually invokes the various neurons in your brain, and it will send the synapses to your vocal tract muscles that will kind of deliver what you intended in your brain. So that's how actually from a psycholinguistic perspective you can define the speech production. But from a functional description, that is from a basic, what are the functional mechanism involved in the production of speech production, you need to dig into the biological aspects of that also. So from that perspective, if you see this left side diagram where the biological organs involved in the speech production are being depicted clearly, there is a lung region from which the air actually exhales. Okay, so the air from the lungs exhales through the trachea, and it will be periodically vibrated by two thin ligaments which are placed at the orifice joining this larynx region, which we call as the vocal fold. So actually this vocal fold in turn will have a resistance associated with it, and because of this air pressure beneath this vocal fold region, and if that air pressure exceeds the vocal fold resistance, what it will try to do is that it will split open the vocal fold and allow the air to pass through this various cavities, including the pharyngeal cavity, mouth cavity, nasal cavity, etc., which are present in the vocal tract system. Now, if you see from that perspective, there are two components that are involved in its production. One is the excitation source that is actually residing at your glottis region, and another one is the vocal tract response. Okay, so we will try to see these two aspects, and how we can actually try to characterize the dynamic variations involved in that. So this is the biological perspective, and if you see carefully over the vocal tract region, there are a number of organs which are again involved in the involved in actually modulating the excitation signal to deliver you the correct voice or the intended utterance that you prefer to utter. Right. So that is from the biological perspective. And if you see that the same from a mechanical perspective, you can actually replicate it in the same way. That is, there is a tool, like if you imagine that a muscular force acting on this tool, actually this is a piston-like thing. You can imagine that the force is acting, then that piston goes up and the kind of air pressure is moved to the vocal fold, and this two thin ligaments which I am actually replicating the vocal folds will actually kind of vibrate, or because of the air pressure that is actually feeding in from the lungs. Okay, so because of that, the air will flow through these cavities, and the pharyngeal cavity, mouth cavity, nasal cavity, overall all these cavities will get involved in its modulating the excitation signal, that they will provide resonance to the excitation signal to deliver either the voiced or the unvoiced sound that we try to utter. Okay, so this is actually the way in which human speech is basically produced from a functional description point of view. And with that description, we can slowly move on to the dynamic variations involved in that. Now, if you talk about the dynamic variation, basically there are two different dynamic variation that happens to the speech production. That is the transition from unvoiced sounds to voiced sounds, and the transition from voiced sound to unvoiced sound. So these are the basic transition that we actually encounter in the speech production, and it is basically due to the interaction of various subsystems involved in the human speech production. By subsystems, what I meant is the various organs or the apparatus involved in speech production, which are the various organs which we saw in the biological aspect of human speech production. So, considering all those subsystems, we actually call this entire speech production as a speech production system. But what happens is that, or what the traditional or the conventional system majorly does is that they consider it as separate entities and they try to characterize them individually. Now, if you see the speech production system as a system, it is basically a complex system. The complex system, by definition, the word complex that has nothing to do over here. That complex is nothing that we deal in the English language. The complexity that is actually that I am referring to here is actually the complex dynamics. The complex dynamics is actually the interaction of nonlinear systems involved in its production. So, if you see that from a complex system point of view, if you try to see the addition of the response from the subsystems will not contribute to the overall activity of your speech production. That is actually the linear theory. But if you see from a non-linear point of view, this superposition principle will not apply over here. So we need to see that from a complex system perspective. I am not telling in the sense that linear theory is wrong. This is actually in the sense that this is a new perspective only. So this perspective may provide good insights about the human speech production, which the linear theory may not provide. So that is the idea that we put forward in bringing in this glottal activity detection or the variation or dynamic variations involved in the human speech production. Now, by digging into more about the dynamic variation, there are actually two kinds of excitation that we know in human speech production. One is the vibration of the vocal fold, which we know as the primary source of excitation, and we also call them as the glottal activity. Now, the other stage is the non-glottal activity, where there is no vibration of your vocal fold, which we try to give in terms of the unvoiced region or the silence region, where you do not have the vibration of the vocal fold in action. So that is known as the abduction stage. We also call them as a non-glottal activity. And discriminating these two regions is actually known as glottal activity detection, and it is one of the primary or the fundamental workflow in many speech processing application. And in that itself, we do have two major events which are known as glottal closure instance or epochs or glottal opening instance. So the significant excitation we refer to as the glottal closure instance, and the minor excitation or the secondary excitation we call as the glottal opening instance. So I have figures for you to kind of see what exactly is these glottal closure and glottal opening instance. So we will be kind of familiarizing with those aspects in a while. So I hope this much is clear to you. And now coming to the fact at how we can actually detect the glottal activity from our uttered speech. So basically, you know that there are only two ways that we can detect. Either we do have the speech utterance with us, or we need to have another measurements like the non-invasive measurements by using like electroglotography signal. So there are actually two possibilities for before us to get the glottal activity. So in that perspective, if you see, glottal airflow is actually kind of represented like this. Now, if you see the your glottis region, if I represent this as a cross-sectional view, you can see that this left portion is actually your trachea, and there is a middle area which is actually replicating your vocal cord, and you have the vocal tract. This is actually the sorry cross-sectional view of your entire system. Now, if you see the air actually flows from the lungs to your vocal cord, and it will get vibrated only when the resistance offered by the vocal cord is less than the air actually pressure exerted by the air. So it will allow the air to pass through it, and the vocal tract in turn will have various resonant cavities inside it. It will provide the resonance to the excitation signal to generate the sound, which we call as vowels, consonants, fricatives, affricatives, stop sounds, and many more, right? Nasals, etc. So these sounds are actually produced in that way. And if you try to see the time domain diagram corresponding to the glottal flow, this will be looking something similar to this. And this is an abstract representation only. It is not the original one. So if you try to see, this is the glottal velocity volume or glottal volume velocity or the glottal flow, and the corresponding speech utterance is represented at the bottom of this figure. So if you can see, there is a small time delay of around 5 to 10 milliseconds because of the uh, time duration it takes from the excitation to reach up to the lips. So this is the speech signal that you have, and this is the glottal flow. Now if you see how we can acquire such a glottal signal, we need to have the technologies like the electroglotography. So once again, so the electroglotography is actually a non-invasive technique. So basically, this is used for pathology detection and providing reference to some of the speech technology application. So its primary importance comes in basically for speech pathology detection. Why? Because you may know the fact that there are n number of voice disorders affecting human beings. So anything that affects the vocal cord will actually disturb the sound produced by the human being. And if we have a mechanism to kind of non-invasively detect what are the abnormalities in that glottal wave, that will provide a what the clinicians an early measure to detect whether the person has some problem or not. So it will assist the clinicians in that way. So electroglotography is not non-invasive technique. So if you can see on the right side, I am placing a microphone, and there are two electrodes which are placed across your neck region to capture your glottal wave. So what happens is that when you utter a sound, what will happen, your glottis region, at your glottis region, the vocal wall will actually try to close. So when it closes, in electronics we know that when the circuit is closed, the resistance offered by that portion will be very low. That means the current will flow through that. So when your glottis is closed, what will happen is that the current will flow through these electrodes, and you will be able to capture your glottal movements as a wave. Okay, so an electrical wave. So that is what you are acquiring through the EGG waveform. But you should remember the fact that the wave that you are uttering is an acoustic wave, a pressure wave, which you are acquiring using a microphone. And by acquiring using a microphone, only you are converting it back to the the discrete time domain, and you are processing it on the computer, right? So that is what we do in our computer. We are not processing the pressure wave asset. We acquire it using microphone, and it will convert your pressure wave to electrical wave, and that discrete time signal is that we process in Python, MATLAB, or whatever tool that you are using. Now, in order to provide reference for your utterance, you need to take this EGG waveform, which is the glottal waveform that will correspond to the utterance that you deliver. Okay, so this is the mechanism that you have for taking the glottal waveform, and these are the equipments that we require, and cost around 1 to 1.5 lakhs. In our center, we do have this equipment, so it has all the required wires and mic, all those things, battery, adapter, everything it has, and you need to kind of use it in that sense. And supporting software will also be there. You need to acquire that. So that's how you take the electroglotography signal. Now, the other method of taking the electroglotography in the speech processing communities, they do inverse filtering operation to find out what is the glottal waveform from the speech signal. So that is another area of research, whether how we can kind of extract the glottal information from the speech signal. That is another area of research. Now I am talking about the electroglotography. Now coming to what the inner details of the glottal flow. So if you try to represent it in abstract form, so this is how a glottal waveform will look like. Okay, so there will be an opening phase, there will be a closing phase, then there is a closed phase. Again, it will repeat because, as I said in the beginning, the opening and the closing, the vibration of the vocal fold happens in a cyclic manner. That's why you have you say in everywhere that your speech is especially in terms of voice sounds, you say that it is a periodic or quasi-periodic waveform. It happens in a cyclic manner, right? So you have this opening phase and a closing phase and a closed phase. And how we can actually kind of relate it to the whether your glottis is closed, the vocal fold is closed or not, you need to take the first derivative. That is what we call the differentiated flow. So I hope you know the fact that this is a time series data. And once you have the time series, what I meant by time series data is that the information is preserved in this samples of values. These are samples of values where the information is stored. And these samples of values represents the vibration of your vocal fold, right? So you, once you have this waveform, if you want to find out what is the time at which your vocal fold vibrate, what you need to do, the easier way is take the derivative of that flow. That is, take the first difference of that flow. So once you take that flow, wherever you have sharp discontinuity, that is the region where you have the glottal closure. Now again, one more factor here we need to understand is that there can be negative spikes and positive spikes. So if the signal, if the glottal waveform is acquired in the positive polarity, because you know that this is actually an electronic device, so basically it will have a positive terminal and a negative terminal. So one, if you place it in the proper way, you will be acquiring it in the positive polarity. So once you have a positive polarity waveform, the differentiated flow will show a negative spikes at the closing region. So you can see that this is the point where the glottis is, the vocal fold is closed, and this is the next point. Okay, now we need to say where it is opening. So the opening points are actually the secondary major excitation. These are the primary excitation. That is why I said in the beginning that GCIs are the significant excitation. So if you see here, the negative spikes are very significant compared to the positive spike. So these are the positive spike, this area, this area, this area. So we can see that the minor and the major excitation, these are the dynamic transition that happens in the when you utter a voiced sound. Okay, so that you can easily capture from the differentiated flow which you acquire from the EGG device. Okay, so basically if you talk about the financial expenses that you require to acquire such a device, it is actually expensive. I would say it is expensive. 1 to 1.5 lakhs is there for that simple device. But what we can do is that there are a number of databases available across your internet, which people have already developed. So along with the occurrence, they do have the corresponding EGG waveform also, and you can take up, then you can do your research. Okay, so it is not that we need to buy that initially to start a research or not. Okay, so existing databases are available. Now this is actually the glottal airflow for a particular speech utterance. So you can see that this is the time domain representation of a speech or a sentence, and the corresponding glottal waveform is actually depicted on the bottom. So you can see for wherever you have this speech utterance, there you have the glottal waveform also, and wherever you do not have any glottal vibration, it's almost kind of nil or a flat thing is there. But there is, you can see that there is a shift in the the waveform. That is only because of the movement that has happened during the acquisition of that waveform. That is, you need to be very static to get the waveform in the zero DC line. But here there is a baseline wandering is there. That is again the terminologies that I am actually telling you. All these are actually various research areas. So baseline wandering is one of the problem with when you acquire using these electrodes. For removing the baseline wandering, there are techniques. So the easier method is that you remove the DC offset, like then you can easily kind of remove that, and you can actually make it exactly like the speech waveform that you see on the top. And only the factor is that in this excitation signal, you do not have the influence of vocal tract response. What you acquire is only the source signal or the excitation signal. Once you have the excitation signal, it will be getting modulated by the various vocal tract filters to provide resonance to that excitation signal, and it will be the utterance that you hear as vowels, consonants, affricatives, like that. Okay, so that's how this glottal airflow will be looking like. Now again, coming to the mechanical abstraction of this human speech production. Initially when people started developing models for this human speech production, they started with this oscillating spring model. That is, they have actually used a spring mass and damping factor to replicate your vocal cord. That is basically they are trying to replicate the vibration of the vocal cord. And when a muscular force acts on this spring, what happens? The spring will try to oscillate, and that will provide you the excitation signal, which in turn will be modulated by this time varying vocal tract filter. Why I say time varying is that as the time varies, the vocal tract will actually change its shape and orientation to provide you the corresponding sound unit. That's how it actually happened. So the important point that we need to understand here is the shape of the vocal tract system actually transforms the raw sound from the vocal fold into a recognizable sound. So that is actually the modulation brought by the vocal tract system to the excitation that will bring in the recognizable sound from the lips. Okay, so that's how the mechanical abstraction will be looking like. And based on this only, people have developed the source filter theory of speech production, which is a very simple model of speech production, which you can easily understand. That is, as I said in the beginning, there are only two kinds of excitation that we assume in the case of source filter model. That is, one is we assume that a voiced sound is produced by a periodic excitation. That is what you are seeing on the left side. And another possibility is that a unvoiced sound. It might be due to a random excitation. So what you see over here is that it is getting multiplied with your time varying vocal tract filter. That is, this input or this input will be getting multiplied with your time varying vocal tract filter. So what happens? This is basically a convolution operation. If anybody of you know this convolution operation, simply that only. That is, you are convolving your input with your system. So that what you get is a system response. So that you can easily represent in the frequency domain as a convolution operation, right? Frequency domain, it will be multiplication, but in the time domain, we say it as a convolution operation. This is represented in the frequency domain. That's why you can see that SZ is equal to EZ into HZ. What is HZ? HZ is the system. What is system? System is your vocal tract filter. That is the physics behind that is the various resonance provided by the vocal tract filter. Actually, what is the response of your vocal tract filter? Okay, so that into your input will provide you the speech. Okay, the corresponding to the sound units that you actually have, the vocal tract will actually shape itself in a time varying factor to provide you the corresponding output. Okay, so this is how the source filter model will work. So now if you see 75% of the purpose that are coming across the speech processing domain are actually based on source filter theory of speech production only, because they assume that this is a very simple model and a lot of actually non-linearities which are there in the speech productions are actually ignored in the source filter model. We take it in the sense of a linear theory only. Okay, so why I say it is in the linear theory is that you are actually separating the the voiced and unvoiced, right? So you actually take it in the separation and then you superimpose it, right? So that is what you are doing. Now, as I said in the beginning, this is actually a convolution operation. So you have an excitation generation and you pass it to the linear system to develop your speech signal. Now, if you take it to the frequency domain, okay, so what you see as time varying signal is the time domain. Now, if you take it to the frequency domain by applying the Fourier transform, what you observe is what? You observe the corresponding spectrum of the sound. So, if I imagine that I am having a voice sound, so voice sound I am actually replicating as what? Impulse sequence. Impulse sequence is what I have represented over here. Now, impulse sequence spectrum will be what? A flat spectrum which is equispaced like this, and you have a vocal tract system. Its response will be something similar to this. So what are these peaks? These peaks actually corresponds to the resonance of your vocal tract system. So you actually do what? You multiply this with this and you get what? This. So this is actually what? The response of your vocal tract system to the input that you are actually applying. So the response will be what? The vocal tract will modulate your excitation signal in a manner that it will look like this. Okay, so this is actually the response of your vocal tract system, and any voice sound is actually characterized in this way only. Okay, So that is about the response of the vocal tract system. And based on the excitation, we do have different classifications of speech sound. That is what you know, that it is voice sound, unvoiced sounds, or the silence region. Okay, so voice sound is actually nothing but the periodic excitation of your vocal cord, and unvoiced is actually there is no vibration involved in its production. Silence means no speech is produced. So based on the excitation, we can actually characterize the speech sounds in that way. And this figure actually kind of depicts the glottal characteristics in those region. That is, this is unvoiced region, and this is the voiced region, and this is part is the silence region. And the corresponding glottal waveform also I am representing over here, and the corresponding first derivative also. So you can see that wherever you have glottal activity, that is wherever you have this speech, that is voiced speech, you do have a waveform in the EGG. Okay, you can see that. But wherever you have unvoiced or silence, you do not have. It's almost a flat line over here and over here. And when you take the derivative of this waveform, you can again see that the discontinuities corresponding to glottal closure instance are very evident over here. This red dotted lines and the blue indicate the GCIs and the GOIs correspondingly. Okay, what are those? Those are the glottal closure instance and glottal opening instance, which are one of the dynamic variations involved in the voiced portions of the speech sound. Okay, so it will not exist for the unvoiced region. That is very clearly because there is no vibration involved. So whenever there is vibration, only the EGG will capture because it has to close. When there is no vibration, you will not be able to capture anything on your EGG device, and your waveform will be getting over a flat line over that region. Okay, so that's why you are not seeing anything over that region. Now, detection of this region has a lot of significance, but it also has certain challenges also. And the separation between this region, that is these voiced, unvoiced, and silence, is basically known as voiced and unvoiced detection, and it can also be understood in the fact that it's also glottal activity detection. Okay, so that's how it will be looking like. And the issues in the voice and voice detections are basically categorized in this way. That is, we actually face difficulty in identifying weak unvoiced sound from silence, because it's almost resembling a silence region, some of the portions of unvoiced region. And it's also very difficult to distinguish weakly periodic sound from unvoiced sounds. Okay, so that is again one of the challenging issue in voice and voice detection. And we need to understand one more factor over here. There is two concepts. One is glottal activity detection and another is voice activity detection. What is the difference between these two is that in VAD or vocal activity detection, it considers both voice and unvoiced as speech and silence and noise as non-speech. But in glottal activity detection, you consider only the voiced region as the glottal activity and unvoiced and silence as the non-glottal activity. So that's the difference between these two terminologies, and they do are separate problems. They are not the same problem. Okay, now coming to the significance, why do we need to do this detection and what is its advantages? Okay, so coming to that, I am just quoting a uh, five applications of glottal activity region. So first of all, it is actually used for the estimation of instantaneous pitch. So once you get the glottal closure instance, they are the points delimiting the pitch region. So once you get that, it is very easy to compute what is the pitch of that person. That is, you take the consecutive difference between that two glottal instance, take 1 by of that, that is, you take the inverse of that, multiply with the sampling frequency, you will get the pitch. That is, in hertz you will get, otherwise we call it as pitch period. If you take it as such, it is pitch period. Okay, so estimation of instantaneous pitch can be done in once you get the epoch location from the glottal activity region. And another advantage is speech synthesis. How it is actually used in speech synthesis, in the sense, once you get these pitch region, you can actually kind of change the prosodic information for the what getting more natural speech. That is, you can change the stress, intonation, etc., and the duration of the pitch. Everything you can change and make your speech more natural. And that is, you can change the prosodic information of the speaker or the person by taking the GCIs locations. Okay, so that is one another advantage. Then coming to the speaker verification, and in speaker verification, what happens is that much of the speaker specific information will be residing in the glottal activity region. So if you are able to fetch those region and will try to analyze or extract features from those regions for verification, that will be more appropriate. Now coming to the emotion recognition, the researchers have already found that source features contribute much towards eliciting emotions than vocal tract thing. So once you have the source features, you can actually augment it with the other vocal tract features to get better accuracy for emotion recognition. In that sense, it is used. And from our center itself, a lot of paper has come across in that direction, like extracting the epoch location, strength of excitation, pitch, etc. of the glottal waveform, and utilizing that along with the MFCC features to get more accuracy in emotion recognition. That is another application. And finally, coming to the speech pathology application, as you know, a person who is having physiological variation in his vocal tract system, that is, if he has some nodules or laryngitis, what will happen is that that person's voice will be getting disturbed in the excitation signal itself, right? So we can easily detect the variation in the voicing signal, that is the excitation signal, by what extracting or by studying the glottal waveform. So that application is also there for the glottal activity region. Now, coming to the nonlinear perspective, why I am talking about nonlinear perspective? The only reason that we actually do a nonlinear perspective is that much of the systems based on in speech technology application prior to 2015, they predominantly focus on short filter theory, which is actually a linear assumption only. The assumption is that they are taking voice sounds as the periodic excitation of impulse sequence, and the unvoiced as an excitation of a random noise. Okay, but actually the point is that it is not that it is not like that. It is actually the nonlinear interaction of various subsystems. So because of that, there exists a turbulence in the unvoiced speech. So if there is turbulence, it is not what linear, it is not a laminar thing. A turbulent flow is different from laminar flow. So turbulence actually brings in the nonlinear effects in the speech, and there has been studies based on the other aspect, like the fractal aspect, the multifractal aspects also. And in 2016, I have found one paper from Journal Society of Acoustics of America. They found that the synchronization and desynchronization of the subsystems involved in the speech production bring in what the nonlinear effect. This is not a characteristics of linear system. This is a characteristics of non-linear system. So we thought that it is more appropriate or advisory to do a non-linear signal processing in the case of speech signal processing rather than going for a linear theory. I am not saying that linear theory is obsolete. Linear theory has its advantages, and it has produced very good promising results in various speech technology application, but they do ignore certain non-linearities in the speech production, which can bring in certain insights if you focus on that. Okay, so that is what our aim was. And we are not the only community that we are focusing on non-linear. It's an evolving community, and we all actually work towards the different applications in speech recognition. And from our center, we basically focus on pathology detection and emotion recognition. Okay, so now coming to the data driven approach, whatever we are doing nowadays is actually data driven approach. So that is, previously we had a theoretical model or analytical model, which basically assumes assumes certain things, that the very simple assumptions we make, and we try to solve the problem. But what we have in that is that we avoid certain complexities and variabilities associated with the real world data. And if you try to follow a data driven approach, we do not require the theoretical model or analytical. We try to infer from the data itself what is the underlying mechanism or the production environment involved in it. So from that perspective, only a data-driven approach is more promising in this speech processing, and that's why we took several state-of-the-art data-driven approaches for analyzing the speech signal. Okay, so to get the dynamic variations involved in it, and these are the problems that we address. First, we tried to address the problem of glottal activity detection from the nonlinear dynamics perspective, and then we tried to analyze the EGG, that is the glottal waveform, to get a proper or accurate estimation of the glottal activity. Because what happens in the traditional or the conventional linear methods of glottal activity detection from EGG is that whenever there is a voicing offset region, that is towards the end of your voice, and there they mostly fail to actually detect the glottal activity part. Okay, and there are occasions where the glottal closure instants get missed during some portions. So these problems or open problems were addressed using the techniques from nonlinear dynamics, and we tried to solve it, and we were able to get good results, and we were able to publish that also. Okay, so that is what I am going to describe in the next few minutes. Okay, so after that, we also tried to get an application out of it, that is analysis of the manner of articulation of stop consonants and vowels in Indian languages. So that also we have done, and we were able to come up with some representations which will tell you what is the manner of articulation of that particular stop sound. Okay, so that is the point that I need to discuss in the coming few minutes. Okay, so the methodologies that I am using here are three methods that I am going to discuss over here. One is variational mode decomposition, another one is surrogate test, and the multifractal determinant fluctuation analysis. Okay, so coming to the variation, so all these are actually used for different tasks. So you can see that variational mode decomposition is actually utilized for the accurate estimation of ground truth glottal activity, and the surrogate test is performed to verify whether the signal is nonlinear or not, and the MFDFA technique is used for detecting the dynamics variation. So I will be following a bottom-up approach. So first we will discuss about the VMD. So I will not go into the whole mathematics behind it. I will just briefly tell what exactly it. So VMD is the expansion for VMD is variational mode decomposition. It's a decomposition algorithm, so which decompose your original signal into a set of subsignals, and each subsignal we call as a mode. Okay, and all these mode will have a particular frequency associated with it that we call as the center frequency. And what is this algorithm trying to do is that it will try to find out the optimal modes which actually represent the entire frequency information in that signal. That is actually the crux behind it, and it's an optimization problem only. So it is all using one of the recent optimization algorithm, ADM. Okay, so the procedure is very simple. So what you do is you take an analytical signal by means of a Hilbert transform to get a spectrum, unilateral spectrum, and you will shift that spectrum to a baseband by mixing it with a complex suspension. So I will not talk about that in detail. This is purely mathematical. So this is actually the mathematics behind it. So you have your signal here. The signal is actually your what U. Okay, so these are estimated modes only. So what it happens is, so this is an optimization problem. You can see that this is actually your constraint, and you are minimizing something. What you are minimizing, you are trying to find out the modes and its center frequency. Modes are denoted here as UK, and center frequency by omega k. Okay, so you are trying to find out the optimal modes and corresponding center frequency, and provided the fact that once you sum up the modes, you should get back your signal. This is the basic idea behind VMD algorithm. So by utilizing that only, we are going to perform the glottal activity detection. So in order to show you what is the crux behind VMD, I took an example over here. So basically, this is a simulated signal. That means we know that in the low frequency region of speech, that is 50 hertz to 500 hertz, we can actually represent the speech as a AM modulated, that is AM FM modulated signal. That is, it is a summation of cosine signal. That is, it's just like a Fourier series you can think of. Okay, so summation of cosines you can. So here I took only two frequency. One is actually 200, another is 400. So the signal and the corresponding spectrum, linear magnitude spectrum is shown here. So you can see that the signal has signal is actually varying like a voice sound over here, and this is the corresponding. I took only two frequency. Now using VMD, I fix the mode as two. Let us take two modes, and let us try to investigate whether we are able to get these information from through the modes. Like, so you can see that the second row, it is actually giving me the first frequency information 200 hertz, second, and the second mode is giving me the 400. So it is actually able to give you the decomposition of your non-stationary signal, and it will be able to tell you what are the frequency component present in that. So that is the idea that we are proposing, and utilizing that idea we propose this method. What is this method? This method is that you are actually decomposing the glottal waveform. This is your glottal waveform, and corresponding spectrum is shown here. So you have the glottal waveform. I decomposed it into three. These numbers are empirically fixed only based on certain experiment. So you may ask why three? Because we have experimented with 4, 5, 6, everything we have experimented, and we come up with an optimal number based on certain matrices. So that is available in the paper corresponding to this title. Okay, so they come up with that number, and when we decompose it, you can see that one of the mode is replicating the frequency information of the excitation signal, that we are trying to capture the fundamental frequency of oscillation in this EGG. Fundamental frequency means that there is a pitch associated with that particular glottal waveform that we are trying to capture using one of the modes. Okay, so here you can see that the second mode is able to capture that. Okay, so that mode is further utilized to get the GCIs and GOIs. So you can see that the same diagram is drawn in a very elaborated manner over here. So this is that EGG, and the corresponding DEG, the first derivative of that is shown over here, and the glottal waveform is also shown over. So this is not the glottal waveform, this is the second mode from this particular EGG. So you can see that the zero crossings corresponds to the glottal closure instant. There is a what, one-to-one correspondence between this negative spike and this blue color into marks which I have shown. Into marks shows the GCIs, and the red rounded one shows the GOAs. So in this way we were able to get what, the glottal closure instance and glottal opening. One more important factor you can notice is that in the DEGG, wherever you have the voicing offset region, that is this portion, the DEG is not able to pick up any spike. But in our method, we were able to detect that portion also. Okay, so that is what the advantage of utilizing the efficacy of VMD algorithm in detecting the GCIs and GOIs. Now we compared it with various state-of-the-art methods. So these are some of the comparison results. You can see that this is one of the popular approach, zero frequency filtering. So in this case, you can see that at this is the corresponding DEG, and this is the result from their paper. So here they do not have a GCIs picked up, but in our work we were able to pick up in that region also. Okay, so we compared it with the different methods, and we tried to find out that the deficiencies associated or the drawbacks associated with those methods were overcome over here. Okay, so these are the comparison. This is the multiple peak in the Hilbert envelope method. So this multiple peak is not actually advisory when you want to detect certain things explicitly. So here you do not have multiple peak because you are actually finding the crossings only. Okay, so that way that is also very it is very giving a very good result. This is another algorithm where the offset region, this is the result from that sigma algorithm. So that region also you do not have the GCAs and GOS, which we were able to get in our VMD based method. So in that way we were able to get a pictorial evidence for our the efficacy of our method, and then we evaluated this method over standard databases. So these are the databases that we used. This is from Festivus data set. So CMU Arctic database, KED timid database, and Keeley pitch extraction. They all contain speech and EGG waveform, and from that we took the EGG waveform and we use a standard measures for evaluating the performance. So this is a standard measure. We fix a Laring cycle like this. That is, you have a reference epoch, and you take the 50% to the left and 50 to the right. That you call as the Laring cycle. And if anything is identified in that region, we say that it is a proper identification. Otherwise, it is a miss. If there are two, we call it a false. And the distance between the original and the estimated one, we call as the what identification accuracy. In that way, we did for the whole database, and you can see the accuracies that we are obtaining are almost 99.27, and the IDA, which is the identification accuracy, is also high in terms of the GCI estimation. Identification accuracy is high in the sense that it is a very low value compared to the other value. So low value means that it is very close. Okay, so we did it for the GOA and GCA estimation. And finally, after estimating those region, we can easily understand what is the glottal activity region. And when compared with other methods have certain deficiencies over this region. And the last one which we show is actually the PMD based method, which we are able to get the proper results. Now that is about the getting the glottal activity from the glottal flow. Now, how when we proceed to investigate it over speech, we need to verify whether the speech is a kind of non-linear or not. For that, we use the surrogate test, which is a very old method. In 1990s itself, it is there. But we utilize the efficacy of that method here to test whether our signal is non-linear or. So this is basically a statistical test where you have a null hypothesis and you test whether the null hypothesis is satisfied or not based on a discriminating statistic. That is what surrogate test means. So we use three surrogate algorithm. So they are random permutation, Fourier transform, and amplitude adjusted Fourier transform. These are three different algorithms which actually based on certain null hypothesis. So null hypothesis is very simple. RP is based on the fact that the time series under consideration is from a what uncorrelated random process. Fourier transform is based on the idea that it is from a uniform Gaussian process. That is, and the amplitude adjusted Fourier transform is based on the fact that it is the time series is not non-linear due to its behavior. It is contaminated with the noise. Because of that, it may be non-linear. So these three null hypotheses we are actually testing based on a test statistic or a discriminating statistic. Now the choice of the discriminating statistic is also very important. I will tell you one example. For example, if you are testing null hypothesis of random permutation, you cannot use mean, because whatever random permutation you do for a time series, mean will be the same only. So you should choose a measure in such a way that it should not satisfy the null hypothesis. Okay, so null hypothesis that is original for the time series. Okay, so we choose a different measure, a non-linear measure, which I will tell in a minute, that is the Hurst exponent. Now, how we reject the null hypothesis, not simply based on certain assumption, it is based on probabilistic idea only. So rejection is carried out in a probabilistic manner using this equation. This is P, that is significance level, 2 into 1 by ns plus 1, where ns is the number of surrogates. Suppose you have one time series, you may take replica of that time series using a proposed RP, FT or AFT algorithm. That many surrogates you will actually bring in, and you will evaluate that statistics for all surrogates. Once you have that, you will have a measure of significance like this, and which is nothing but T naught minus mean of TS by sigma S. Okay, so T naught is the original statistic. The TS is actually the it's a distribution. TS is a distribution. That's why you take the mean of that and divided by the standard deviation, you will get the measure of significance. And once you get that, you plot it. You plot it as a histogram. So you can see that this red color line is actually the original statistic for the original time series. So I am testing here. Here A, B, C are the three surrogate algorithms. So what is we are trying to find is that whether the null hypothesis is satisfied or not. If it is not satisfying, what is the inference? Inference is that it is from a non-linear system. If it is satisfied, it means that it is from that null hypothesis, right? So that is what we are trying to do, and it is a probabilistic approach only. Okay, so in this we are showing that it is this example. This is an example time series KDT00 taken from a timid database. For that time series data, we are showing that it is not belonging to any of these blue color thing. That means that it is not following any null hypothesis. It is a non-linear. It is from a non-linear process. Okay. Now, if you see, we need to verify whether it will work for the linear theory. So what we did a linear prediction analysis, that is LPA. Linear prediction analysis assume that it is from a source field theory of speech production. So in that case, you can see that the FT surrogate is actually satisfied, or the FT null hypothesis is satisfied. That means that it is from a linear process. Okay, so that also emphasizes the fact that LP analysis is a linear method of analyzing the speech signal. Now we investigated in that way and we established that the speech signal is non-linear. Now coming to the detection of the dynamic transition, we use multifractal determinant fluctuation analysis. So this is motivated from our nature only. So you can see that there are n number of things that are present in the nature which shows this fractal nature, that is its cell similarity. Fern leaves, broccoli, lightning, whatever you call, these things actually exhibit the property of what cell similar. They actually show, if you zoom in, they again show the same structure. Okay, so what we try to do is that whether this exists for a time series data also. Actually it exists, and we need to show, like we need to kind of dig in how we can show that whether the cell similarity exists for the time series. So this is an example that I am showing over here. It's not speech signal, this is a example simulated time series data. So you can see that this portion replicates the entire time series again. So there is a cell similarity associated with the different scales. So this cell similarity we in turn calls as the scale invariance of that time series. So if you are able to find the scale invariance of the time series, we can actually categorize it into monofractal or multifractal. So monofractal and multifractal is only different in one way. So if you have a time series xt, if it satisfies a relation like this, that is x of ct is equal to c raised to h into xt, where xt is your time series. So where h is actually a exponent, which is actually known as a Hurst exponent or a power law exponent, and c is simply a constant only. Okay, so if it satisfies this relation, and if h is a constant, we call it as a monofractal signal. If h is a distribution, we call it as a multifractal signal. So this is actually the idea of monofractal and multifractal time series. Now how do we find that? Is we actually try to find the fluctuations in the signal. And how do we find fluctuation? You try to find the root mean square value, RMS value. And that is not simply root mean square, it is q order. You find it for different q order. There is an advantage of using different q order. I will tell you with this example. So you can see that there is a blue color time series and a green color. Blue is actually the multifractal and green is actually the monofractal thing. So what is the advantage of finding the RMS, root mean square value, for different q order is that when you have lower fluctuation, that will get emphasized in the negative q order. When you have what positive, that is when you have larger fluctuations like this, that will get amplified in the positive q order. So by utilizing this approach, you are able to get what the lower order fluctuation and the lower fluctuations and the larger fluctuation, because those are the characteristics of speech signal also, because speech signal actually have spatial and temporal correlation. Okay, so this property we can actually investigate by estimating its q order RMS and then plotting it along with the different scales. So you can see that these are all conceptual diagrams only for the time series that I am showing over here. I will show the original time series for speech in a later point. Okay, so you can see that for the multifractal time series, for different q order, you have different lines like this. This is actually a logarithmic plot between your fluctuation and the scale that you are fixing. Okay, and this is again for monofractal. But there you can observe one factor: they all have a constant slope. Here the slope is changing. This slope is what I meant as the Hurst exponent, that h value over the c. Okay, and for a white noise, if it is a random noise, it will be again a constant, and it will be 0.5 also. That constant value is a 0.5. Now that is actually represented after a mathematical transformation like this, which is known as Legendre transformation, a multifractal spectrum. So you can see that for monofractal, it will be something like this red color. This is white noise, and this slope E1 is actually the multifractal. So corresponding spectrum is shown on the right side. So when you have a multifractal signal, you have a wider you have wider spectrum. And for monofractal, you do not have a wider one, a very small wide width only it will have. And for random noise, you have it around 0.5. Okay, so that's how this will differ. Now I experimented it with the real life signals. So this is a periodic signal generated at 150 hertz. First one. Second one is Gaussian white noise. Third one is signal from a Lorentz system, which is a chaotic system. So you can see that whatever we have identified as fractal characteristic, it is also replicated over here. So for periodic, it is almost close to 0. Random noise, it is almost close to 0.5. And for multifractal, you have a wider width in the spectrum. Okay, so that is a spectrum. Okay, so that's how the spectrum will look for these kinds of time series. Now coming to whether it is relevant for speech, we can investigate that. So what we did was we investigated with the original signal and a simulated signal. Blue is original and this one is actually the simulated version. B is actually the simulated version. How I simulated is based on the LP analysis only. Okay, so sorry. Okay, so what we are inferring over here is that the spectrum corresponding to this voice sound and the simulated version both look almost the same. They both fall along each other, right? So you can see that the black and the blue are almost falling on the zero, towards the zero of your scaling exponent x cube. Okay, singularity exponent x cube. So you can see that it's almost behaving like a monofractal thing. Now, if you come to the unvoiced sound, this is an example unvoiced sound taken, and the correspondingly I have simulated another one. Okay, so you can see that this is simulated and this is the original one. So you can see that for the simulated one, it is closely following a monofractal structure, but for the original, it is multifractal. Okay, so what is the inference from that? This is that the linear prediction analysis actually assumes that what this unvoiced sound is actually due to random noise excitation, or it is not due to turbulence, but due to turbulence only this nonlinear effects is coming, and that brings in about the multifractal nature of the original, the blue color one, which is not evident in the simulated version. Okay, so that is one of the things that the LP analysis ignores. Okay, so which we are trying to find out. And now based on that, we experimented with the different sounds. So these are sounds from the database itself. So different voice segments are taken. This is sound S sound. So you can see that for this sound, it is showing the random excitation. This voice sound, it is showing the almost a monofractal nature. And for this S sound, it is showing a multifractal nature. So what is the inference from this is that voice sound exhibit a monofractal nature and the unvoiced sound exhibit either random or turbulent. Both can happen. Okay, so that was the finding from our study, and based on that study, we developed an algorithm to find the glottal and glottal, which is nothing but you are estimating the Hurst exponent, that slope value you are estimating. Based on that Hurst exponent, you are trying to find out whether it belongs to non-glottal or glottal. And we are able to find out that this is actually the bottom row actually shows the estimated Hurst exponent for this corresponding speech utterance. You can see that wherever you have glottal activity, that portion you have Hurst exponent is almost close to 0. In all other region, it is higher. Okay, so we can easily estimate that using a simple thresholding scheme, and we actually used empirical studies to fix the threshold, and here we fixed it as 0.1. Okay, so for the data set, we evaluated for different values of threshold, and we tried to come up with the optimal value. So that's how we solved, and finally we evaluated the performance using standard measures, which is nothing but voiced, unvoiced error. Okay, and voicing error and unvoicing error were also calculated, and these are the results obtained when compared to the state-of-the-art system, which was it was a promising result based on the comparison. Okay, so 93.73 and 93.21 are the obtained results for two data sets which I have shown in the previous session slides. Okay, so in that way that work is completed, and based on that we motivate ourselves to do the analysis of stop consonants and vowels in Indian language. So this is again a multifractal approach only. So as all of us know about this categorization, sound units. So sound unit, basic sound units we can actually categorize into vowel and consonants. So vowel categorization based on the fact that the vocal tract is wide open without any constriction in its production. But when you are uttering a consonant, obviously the vocal tract have a constriction somewhere along its length, and based on that you do have different types of stop consonants, right? So that sort of analysis we are going to perform in the next experiment. So here what you are doing is we are trying to find out the manner of articulation of different stop sounds in Indian languages. So here I took only four categories: velar, post-alveolar, dental, and bilabial. So you can see that in our Indian languages there are only two parameters which actually determines the manner of articulation, which are voiced, unvoiced, and articulation and unarticulation. So based on that, you do have these 16 categories of sound: ka, kha, ga, kha, ta, tha, da, tha, like that. Okay, so you can see that ka belongs to unvoiced, unaspirated. This kha belongs to unvoiced, aspirated. Ga belongs to voice, unaspirated, and kha belongs to voice, aspirated. So what we are trying to put forward here is that can we find out this manner of articulation without the knowledge of its voicing or unvoicing region. Okay, so basically what in traditionally or conventionally what people does is that uh, the the region from the glottal activity to oral activity, that is a voicing onset time is there for all these sounds. So based on that VOT only people are trying to kind of characterize these sounds, because when you talk about ka, it starts with an unvoiced occlusion, then there is a burst, and then after that there will be this voice onset time, and after that there will be that r sound. You cannot produce ka without that r, right? That r sound is also coming. So that will be the glottal vibration coming. So if you talk about that velar sound itself, the place at which that construction happens is the velar region. And so that's why I'm showing this picture, because all these categorizations are made on the base of place of articulation and manner of articulation. So what we are trying to solve here is that can we estimate that manner of articulation from the signal itself by estimating the multifractal characteristics. So what we did was a similar approach that I shown earlier. So you can see that I am using MFDFA to find that spectrum, and if that spectrum is actually showing a monofractal nature, it is actually we found that it is a vowel sound. And if it is showing a multifractal nature, that definitely belongs to a consonant sound. And once you get that inference, you can compute the spectrum width, and based on that you can actually characterize the manner of articulation. That was our proposal, and this is also accepted, and this paper got the best paper award in an international conference. So you can see that basically what the initial experiment what we did was taking a vowel. Okay, so vowel R sound is taken and consonant Ka is taken. You compute the multifractal spectral width of it. You can see that the blue color line is actually the showing the monofractal nature of that vowel sound, and the red color thing shows the multifractal nature of that sound, Ka sound. Okay, so once you get this inference, you apply it for the stop sounds in that category. Okay, so what is the inference from all this is that you can see that the diagrams with along with its legends shows the multifractal spectral width. So you can see that in the velar sounds by velar, dental, bilabial, and post-alveolar, this green color thing, green color is actually voiced unaspirated, and the red color one is the unvoiced aspirated. So unvoiced aspirated is getting what more multifractal nature, and voiced unaspirated is getting monofractal nature. So what is the that is the major inference that we can see here, and these are distinguishing the manner of articulations of the different stop sounds in Indian language. So in summary, the results can be found formulated like this. So you can see that the sounds with aspiration and unvoicing will have more multifractal nature. Sounds without aspiration and voicing, they will be monofractal, and in between them will be having what the slighter variation in the multifractal spectra. They belong to either unvoiced unaspirated, or voiced aspirated. Okay, so in that way they differ, and these are the conclusions from that. The result shows that the variation is partial with respect to manner of articulation, and all four places of articulation with the broader burst share the aspiration aspect. That means whenever you have aspiration, it will share what it will actually bring in more width in your spectrum. Okay, the one with voicing and not aspirated always shows the trend of a vowel, but it is not definitely a kind of what vowel nature, because it has certain turbulence inside it because of the influence of the excitation source and the vocal tract. So the conclusion from the whole study is that data-driven methods extract relevant features directly from the speech for accurate characterization of its dynamic character. And this is the first study that came in the view of multifractal analysis to detect the transitions in speech. And we showed that the Hurst exponent estimated using that analysis, MFDFA, can discriminate this region, glottal activity and non-glottal activity. And we also show that this unvoiced sound is not only random, they exhibit both multifractal and random noise like nature. Okay, and glottal activity region exhibited loss of multifractal nature. It's more towards mononoid. Okay, and then we can also find that the spectral width is a promising measure for
Hello.
characterizing the manner of articulation in stop sound. And the study based on VMD
Hello.
help us to estimate the
Hello.
glottal activity more accurately compared to the state of the art methods. Okay, so with that, I conclude
Hello.
my topic on data-driven methods for identifying the dynamic transition in human speech version. And thank you. And these are the references which I have used for preparing this presentation. And if you have any questions, you may ask. Thank you, sir. Thank you.
Phonetics, it was even the articulatory phonetics too. Uh, at the outset,
Thank you, sir. Thank you, sir.
yeah, somebody is speaking. At the beginning of his lecture, Dr. Yojilal has
Sir,
presented the
one person has
biology
to
of
close.
speech sounds. Somebody has. Hello.
Sir,
Hello. Please, could you please? Uh,
sir, one mic should be
yeah,
mute.
muted. That has to be muted. Somebody has unmuted.
Yeah. Someone has to mute
I think
their mic.
Professor Rajendran has unmuted his mic. I think so.
Mm.
Better, please. Now it's okay. Uh, Professor Jodilal has nicely
Yes.
presented his ideological stance with regard to the article politics. At the outset, he has explained how the human speech sounds are using our own biological. Of course, our biology is designed for some other purposes. However, we exploit those organs to produce speech sounds. He has in detail explained how a speech sound is produced from starting from lungs to what you call oral cavity through the glottals or vocal cords and all. He has nicely explained the manner of articulation and point of articulations. After that, he touched upon the physics of human speech sounds and how it could be measured using different what you call instruments, grams, sonograms or glottograms. Many instruments he has used to measure the quality of the speech sounds, and thereby he identified the best qualities of the speech sounds. In turn, it could be imbibed in the brain of the computer. Then he has taken some sample from South Dravidian languages, and he has analyzed the speech sounds, how it is produced when it is unvoiced, how it is produced in voiced, how it is produced with aspirated sound or without aspirated sound. Such a way, he has classified, he has given all detail about the physics and what you call biological aspects of speech sounds in production, in reception, and what you call in transmission also, in production and transmission and reception also. And he has nicely touched upon different research methodologies he has applied, of course, really beyond our head, and to some extent beyond our head. I hope that people might have got a good idea over the production of speech sounds using the physics and all. Okay. Now the floor is open for discussion. Any queries? Many politicians are also sitting here. Of course, Professor Ravi Shankar is there, and he will be in a position to comment on this his performance. And if he has any specific query, let him raise his queries. And of course, Professor Jyotilal will be in a position to answer his queries. And not only Professor, what you call Ravi Shankar, another member can also participate in it.
Thank you, sir. Thank you for your encouraging words, and I am open to any questions.
This is not the question. Am I audible?
Yes, sir. Yes.
Okay. This is not the question, but I am Dr. Benish from CDAC Pune, and you explained so many things, very good things, source filter model and everything, and the modulation of this source. Can you? The modulation of the source filter model for text-to-speech system. Actually, the source filter model implemented by not Rabiner, Fujisaki model that is applied for the agglutinative language, especially for Tamil, Malayalam, Japanese, and Telugu, etc. That's a good approach. That is a biological, like a vocal apparatus model. Vocal apparatus
Yes, sir.
model means that won't be applied to other language. So somehow in Indo-Aryan language or some other English or some Chinese note, German or something. That is one thing. That is a vocal apparatus model. And another one, Tyler also made the different model they implemented for the text-to-speech system. That is the distinction. My one doubt is that you are doing the research on this manner of articulation, the voiced and voiced aspirated, unaspirated sound. Actually, in Tamil also, in Malayalam also, probably you are Malayali or Tamil, I think. Suppose
Malayalam. Malayalam, sir.
Malayalam, yes, Malayalam. In Tamil also, Malayalam also, with ka, ika, ga, ika, nga. Pa, ifa, ba, ifa, ma. Ka, ika, this aspiration, actually the aspiration is not existing in our language. Suppose if in a standard language, if I teach someone that Malayalam or Tamil, then Tamil is not there, unaspirated is not there. If I teach someone in standard way, then only I can utter this aspirated sound.
Aspirated sound.
Otherwise, if you take the dialect or something, or somebody speaks something, they won't make the distinction. So that is to be considered. That my suggestion is that
yes,
it is to be considered for your study. That means the dialect is very difficult to process. That is very difficult because if you in Madurai also, Tamil in Chennai also, different region, you can see that the different variants of Tamil or Malayalam language. That is to be considered.
Okay, sir. Okay, thank you for your comments.
Jyotilal, your presentation really was interesting. I really enjoyed it, especially the first part of it and the last part of it. Actually, I could follow, and in between, it's a bit technical for me actually. Otherwise, of course, especially last part of it, you make a difference between closing and all, the graph and all. That's very interesting. Especially, of course, we are trying to actually exploit the what you call the tract acquisition, acoustic point of view. Actually, for certain things, they are very interesting. Actually, congratulations! You did a wonderful presentation. Thanks to you.
Thank you, sir. Thank you very much.
Yeah, I'm Ravi Shankar. Mr. Jyotilal.
Yes, sir. Yes.
Thank you for your nice presentation.
Thank you, sir.
Now you have given, he said, this is the first kind of approach that you have developed this model, which is much appreciated. It is a good thing. Anyway, that we as a linguist, not a computer scientist, So we understand so many things from what you call it biological point of view, but you are given that a kind of computer person's attribute to the biological activities, and
Yes,
uh,
sir.
and it's a very good thing, very good approach. I
Thank you,
appreciate
sir.
this thing, and there are so many terms and they have used, so it will take some time to get into those familiar with those things. Otherwise, a very good presentation. Congratulations.
Thank you, sir. Thank you, sir.
I'm Dr. Umaraj from Department of Linguistics, Madurai Kamaraj University.
Yes, sir.
The presentation was very good. That it was we recorded all those your paper.
Okay, sir.
So thank you very much for
Okay, sir.
giving that what is meant by data-driven approach and all those things.
Okay, sir. Okay, sir. Thank you very much, sir.
Actually, our students wanted to we want to establish a speech center like this
Okay, okay.
only in linguistic department. Every linguistic department should have a speech technology lab. Then only
Okay, okay, sir.
so
Okay.
you given some inputs. So whenever we want to establish those lab also, so if that is happen, then you have to help us. This is the one
Okay,
thing.
sir. Surely,
Then
surely.
another thing is that what are for example process.
Sir, I'm not able to hear you. Sound is
Then
gone.
prosody and another for example for example first sentence they will give emphasis for a particular word, then the same word the dog bite him, like that it will come. So when they will give emphasis for the dog, in second sentence they will not give emphasis for the dog, they will change it. So the prosody also will play a major role. So whether with your data-driven approach or you are capturing certain things, no, you given some results. Whether it will affect prosodic thing or it will not affect. Thank you very much.
Sir, basically, this approach, we are not actually touching the prosodic information. We are actually extracting the information as such. Like we are not changing it.
Okay, thank you.
Because basically, if I want to change this, once I got the glottal activity region and the epoch or the GCI location, I can change it. For example, if I want to do a voice conversion or an emotion conversion, I can change the pitch duration, stress, etc., strength of excitation, everything, and I can convert a neutral sound to an angry sound to a neutral one, like that.
Okay, okay, thank you very much. Okay, thank you.
In fact, Dr. Uma, he had not touched those prosodic aspects. He has stopped with the articulative vision like aspirated, unaspirated, and voiced, unvoiced sounds. And there is stress on the manner of articulation. But it is difficult. They have to go still further to include the prosodic features. For example, the example you have given is only the matter of stress or accent that focuses the particular information according to the speaker.
So those things also there is what Chomsky is telling, no, the particular parametric, different language has a parameter. Some of the universal properties will be there, and specific to the particular language will be there.
Yes.
So that should be, for example, our the Hindi have 4 casts, K, voice, aspect, all those things there. For Tamil, we don't have those things. Only unvoiced things are there. So those features also will affect the results. I don't know. We have to see. Thank you.
Okay, okay, sir.
Thank you.
Tamil, Dr. Uma,
Yes, sir.
yeah, actually in Tamil, we don't have a voice in the script, but in speech we have the voice articulation. That is one
Yes,
thing.
sir.
Even I feel the aspiration and unaspiration in different Indian languages need not be the same. It should not be the same for Malayalam and Hindi or Telugu and Kannada like that. So accordingly, they have to work out the variations using the model that has been proposed this by Mr. Lal.
Okay, okay, sir.
Okay. Thank you, sir. Thank you very much.
Thank you.
Yes, yes.
Yes.
Let me speak. Sir, are you concluding? Sir, let me speak. Yes, what you, sir, sir, explain the concept is very accurate things. That means the um, suppose that this dialectal variation, we cannot find out these aspirated and unaspirated, especially in standard language. Standard language you can find, but in the ordinary conversation, ordinary utterance, if I speak to someone, Malayalam also you cannot find. Even Tamil is, but in Hindi you can have that. When aap jao, or aap sikho means that the aspirated, that is their nature, aspirated, unaspirated properties in Hindi. There. Even in Marathi also that thing. And the important thing is that the very important the emotional extraction to the suprasecundal features. That is a very important intonation, tempo, and some other features that will also that is also a good research area, intonation and emotion. Okay, please carry.